This array factor has some really interesting properties. It is first, it's a periodic sinc function. It has a maximum every time the denominator goes to 0. You might think it would diverge then because the denominator went to 0, but in fact, the numerator has a 0 there too, and you can use L'Hopital's rule to make it into a actual defined value. It's not actually undefined. And in fact, its maximum value is n. And it happens when the argument of the bottom is a multiple of pi. Second, it has zeros every time numerator is 0, which makes sense. I mean, except at the maxima. Which happens when kd over 2 cosine theta is equal to some multiple of pi divided by n. It's often easier to look at this on a graph and to see an example. So we're going to define a new variable, psi, to be kd cosine theta. Then if we rewrite that, the array factor in general of a uniform linear array is sine of n over 2 psi divided by sine of psi over 2. If we plot the array factor as a function of psi, and I'm going to plot the absolute value because for antenna applications, that's really what's most relevant. We have a maximum at psi equals 0. We'll have another maximum at psi equals 2 pi. And like I said, the value of these maxima will be n. There could be another maxima minus 2 pi. And at any other multiple of 2 pi that is within the range, which we're going to talk about in a minute. And then we'll have zeros at these locations where psi equals 2m pi divided by n. So let's choose n equals 5 and see what that turns out to be. So if 2 pi is actually 10 pi over 5 here. We're going to have a 0 right there at 2 pi over 5, another one at 4 pi over 5, another one at 6 pi over 5, another one at 8 pi over 5. So actually I've got the width of these a little bit off. These main beams should be twice as wide, but that's okay. Anyway, we've got side lobes that will pop up next to the main beams. It'll look like that. And the same thing on the other side, on the negative side. Now here's the thing. Not all of the values of psi translate to angles that actually exist, to values of theta that actually exist. Because remember that psi is equal to KD cosine theta. Oh, I need to move that. I'm going to write it up higher. Not all of the values of psi on this plot translate to values that actually exist. Because remember that psi is equal to KD cosine theta, and cosine theta is less than or equal to 1 in absolute value. Which means that psi can only vary between plus and minus KD in values. And this plot may extend wider than that. For example, remember that K is 2 pi over lambda, so if we choose D equals lambda over 2, and then KD is equal to pi. In that case, the values of psi that we can actually see here are just within this blue rectangle. I can actually draw this on a polar plot by projecting it down and drawing a circle whose radius is pi on this plot, so whose extent is just from minus pi to plus pi. I'm going to draw the top half of the circle for now, because since this is a linear array, the radiation pattern is going to be symmetric on either side of the z-axis. It's rotationally symmetric around the z-axis. But here's how we can draw the pattern of this without actually doing any additional math. We project all of the zeros and maxima locations from the Cartesian graph down onto this circle. And we draw radii from those points to the center of the circle. Then we also preserve the magnitudes, the heights of these things. So we turn the height of the main beam into the radius value at the location of the maximum. So we can draw that main beam to look like this. The next one, we take this height and transfer that height down onto the graph. So that next side lobe looks like that. And the next side lobe looks like that. So the radius is about there. The array itself in this picture is sort of passing through the image horizontally. Imagine that these are the ghosts of the array elements. Although I've drawn too many, there were only 5. So let's say that there are 5 array elements. And the antenna pattern, the array factor is rotationally symmetric around the axis of the array. So you can imagine each of these lobes is sort of a donut or a conical donut shape. If you were to take this cross section and rotate it around the line along which the elements are distributed. So our array factor looks like that. If I choose a different value for KD, I can increase or decrease the radius of this circle. I'm going to go back up and draw the relevant rectangles on the Cartesian plot. So if I choose KD equals pi over 2, which would translate to a spacing between my elements of a quarter wavelength instead of a half, then I would only end up with this much of the rectangular plot inside my field of actually viewable angles. On the other hand, if I choose KD equals 2 pi, which would translate to a spacing between my elements of 1 wavelength, then the radius of my circle and my angular field of view would include this much of my graph. And this brings up an interesting point. Now we can see not just the main beam maximum, but also this other maximum over here, which is split in half on either side, but this one joins together on either side when you do it this way. This second maximum is not another main beam because it's not in the intended direction of the main beam. This one is called a grating lobe. Which is a term that antenna engineering has adopted from physics, from the laser and grating experiments, where you shoot a laser at a grating, a diffraction grating, and then what you get out is an interference pattern that also looks just like a periodic sink, because it is. And these are called grating lobes for that reason. So as you let the spacing between your elements get larger, you begin to see grating lobes in your array factor. And in general, these are not desirable and you want to avoid them. There are some times where you can sort of design around the fact that they exist, but in general, they're not something that you want. So you can see that as the total length of the array increases, as you increase the value of D, or as you increase N, ND being the length of the total length of the array, the amount of this function that you can see sort of increases. N has the effect of squeezing zeros together. And D has the effect of increasing the range of psi. And together, L, the total length of the array, is known as the aperture, which is another term that we borrowed from optics. If you're talking about a camera or a lens or something like that, it is the opening that light goes through. But since in antenna applications there's not always a literal opening, we sort of generalize that concept to be the area that radiation comes out of. Or in an array context, the area over which the antenna elements are distributed. So if I have an array, let's say a two-dimensional array, and I have elements that are arranged on a grid within this area, that rectangular area that I drew is the aperture for the array. In our next video, we will talk about a graphical way of generating array patterns, sort of a generalization of the projection onto the circle that we did here. And then we'll talk about how to implement beam steering. And later we'll also talk about 2D arrays rather than linear arrays. So what happens if you arrange your elements in a grid on a planar area?